Hello everyone, welcome back. Imagine a city where thousands of people live and work. To function smoothly, they need communication, email, phone call, and face to face meetings. Similarly, in an operating system, multiple processes run simultaneously at the same time. And for them to work efficiently, they need to communicate. This is where inter-process communication comes into play. In today's video, we will break down what IPC is, its different models and schemes, and how processes are created and managed. By the end of this video, you will have a strong understanding of how processes work together in an OS. So let's get started. Firstly, what is inter-process communication? In any modern operating system, multiple programs can run at the same time. Each of these programs is called a process. So, process needs to communicate when they share resources, synchronize tasks, or exchange the data. The OS will provide special mechanisms to allow inter-process communication. The key reason for inter-process communication is the sharing data. That is, one process generates data while another analyzes it. Then synchronization, ensuring a file is not modified by two processes simultaneously. Then we have event notification, that is, letting one person know when another has completed a task. A real world example of this is think of a banking application where one process handles user authentication, another handles transactions, and another updates the account balance. These processes must communicate efficiently to ensure seamless banking operations. Now, let us look at IPC models. How do processes communicate? There are two main models of IPC. The first one is shared memory model and the second is message passing model. So, in shared memory model, in this model, multiple processes share a portion of memory to exchange the data. One process writes the data into the shared memory while another reads from it. The benefit is that fast communication, since no operating system intervention is required once memory is allocated. There is also a challenge that it requires synchronization mechanism like semaphore or mutex to prevent data corruption. An example of this is a video streaming application where one process reads video frames from a file and another displays them on the screen. Shared memory ensures efficient data transfer. And real world analogy is think of a shared Google Docs file. Multiple program people can read and edit it in real time. Then we have the message passing model. It means that message has to be passed. Processes send and receive messages through the operating system only. The OS provides a message queue where one process writes data and another reads it. Benefit: it is work well in distributed systems where process runs on different machines. The challenge is that it is slower than shared memory because messages pass through OS and it is a must that the message passes through the OS. An example of this is a client server model. In the client server model, where a web browser, that is a client, requests a web page to the server and a web server sends the response. Or you can say sending a letter through a postal system. The message is stored in the mailbox until the recipient collects it. Moving further, let us look at IPC schemes. How is IPC implemented? So the IPC models are implemented using different schemes or mechanisms provided by the operating system. Let us discuss the most common ones. The first one is pipes. Water pipes. Pipes are used for one-way communication between the process. The data written into the pipe by one process is read by another. It works well for parent-child processes. For example, like a water pipeline where water flows in one direction only. Then we have message queues, a queue where messages are stored until retrieval. A definition, a data structure where messages are stored until the receiving process retrieves them. Benefit, it allows communication between unrelated processes. Example, email services for message queues. The emails remain in the server until the users downloads them. Then we have shared memory. So, what is shared memory? It is a block of memory shared by multiple processes. It requires synchronization mechanism like semaphore or mutex to prevent the conflict that arrives. An example is DBMS, where multiple processes read, write data simultaneously. Then we have sockets, two processes communicating over a network. It is used for process communication over a network, that is between different computers. Example, web application, where a browser and a web server communicates over TCP IP sockets. Then we have signals, a process sending a signal to another process to terminate it. A lightweight way to send notifications between processes. An example is the kill command in Linux sends a signal to terminate a process. Now, let us look at process generation. How are new processes created? Process in an OS are created using system call. A process that creates another is called a parent process, and the newly created one is the child process. What are the steps in the process creation? Firstly, forking. Forking means the parent process. Forking means the parent process creates a child. Then execution. The child can execute a different program using Excel. Waiting. The parent can wait for the child process to complete using wait. Termination. The child process completes and is removed from the memory. For example, when you open a new tab in a web browser, a new process is created. So, fine. The next one is process termination. How do process end? A process can terminate in different ways. First one is normal completion, when it finishes its task. Then we have error or execution due to a bug or a system failure. Then we have forceful termination. Then parent process kills the child process if needed. For example, when you close an app, the process is terminated. So, to summarize, inter-process communication allows multiple processes to work together efficiently. The two main models are shared memory and message passing, implemented using mechanisms like pipe, message queues, and sockets. We also learned how processes are created and terminated in an operating system. Understanding IPC is crucial for software development, especially in software cycles. So, if you like this video, hit the like button and subscribe button and comment below if you have any questions. Thank you. See you in the next video.